Okay, I guess we're going to get going. Introduce a good friend of mine, Salil Raje. Actually, I was on the board of one of his startups back in, I think it was 2001, right? Many years ago. And got to work with him as my partner in crime, trying to get things going like this embedded vision initiative. And so he's going to talk today, as you see, about the advantages of combining edge and cloud processing for visual intelligence. Okay? So I'm going to set this so when it says 0, you really have about 5 more minutes left, and then 5 minutes of Q&A. So we'll keep track of time and try to give some time for questions. Talk to you soon.
Okay, thanks, Steve. Good afternoon. It's a great pleasure to be here in front of all of you embedded vision enthusiasts. We in Xilinx were actually one of the founding members of the Embedded Vision Alliance. And back a few years ago, it used to feel like a very small club, mostly focused on industrial automation and some visual inspection. Of course, now with so many advances in smart systems and all the research in deep learning, it does feel like the possibilities are endless. And this conference and the way it's grown, it is truly a testament to all the opportunity we see going forward in front of us. Now, one of the key decisions in these systems that system designers have to make is where do they put the vision processing? Do they put it on the edge or do they put it on the cloud? Increasingly, though, in our own customer base, what we are seeing is system designers are using a combination of those two, a combination of edge and cloud processing, and we call it hybrid architectures. So what I'm going to do today is explore some of the factors involved in choosing these combinations, the edge and cloud processing, deciding the hybrid architecture, and some of the solutions required in putting together the right blend of edge and cloud processing in these hybrid architectures. So the agenda for me today is first talk about some of the applications we see in our customer base, some of the architectural trends we see in our customer base with these hybrid architectures, some of the challenges system designers are facing in choosing the right architecture, and then we'll end with a discussion on what's needed. What are the solutions required to make sure that when we create these vision systems, these hybrid architectures, they are practical and cost effective. So let's start with some of the applications we see in our customer base, some of the architectural trends we see. The first one here is something that we see on the edge, and this is driver assistance. This is, of course, a killer app in the vision world. We have seen a huge progression of driver assistance from very simple warning-based systems where the driver is alerted to some impending danger. For example, there could be a stopped vehicle in front of the driver. But what we are seeing is a progression from those systems to very complex, very intelligent systems that respond based on the context in real time. And the response could be either braking or steering or maybe parking assistance. In each of them, the response time has to be within split seconds. In fact, it has to be within a latency constraint. What we see today is about 100 milliseconds. Now, given this latency constraint, most of this processing has to be at the edge. Now, here I've shown you one example of an embedded vision system. Here, the EV system, the embedded vision system, has to detect the pedestrian and then chart the path of the pedestrian. And then it has to respond using either braking or then steering the vehicle to the right location so that it does not collide with the pedestrian or with any of its surroundings. Now, because of the latency constraint here, because of the response time needed in this system, you have to put this on the edge. And because it's part of an embedded system inside the vehicle, there are severe power constraints. And the power budget that we see most of the time in these systems is around 5 watts. There are also cost constraints. Mostly we see the cost associated with this about $10 to $40. Now let's look at the other end of the spectrum. Some of the applications have to be implemented in the cloud. So in these applications, latency is not necessarily a severe constraint. But here throughput, performance, compute performance, and storage, disk storage capacity can be a significant factor in putting these applications in the cloud. Now Google image classification, of course, is a classic example of this, where you can upload a painting, picture of a painting from your phone, and then Google will identify that image based on its huge digitized art database. Well, here's another example. There could be MRI centers that upload significant amount of data to a private cloud. So these MRI systems could have slices, images that are slices of the brain. And together, of course, you can render it as a 3D. But there's a lot of research going on right now on deep learning that look at these images and spot anomalies or even detect some of the suspicious areas for radiologists. Now, latency in this scenario is not a huge constraint, but you may need some amount of speedier response time for the radiologist. Sometimes you need the results really quickly. But here, power could be a constraint, because power could translate into platform as a service cost. So again, you could have throughput constraints, you could have power constraints, and then another factor here would be platform as a service cost. So you saw some application that is purely on the edge. Now this application is purely in the cloud, but let's look at an application that is not so clear-cut. So home security systems. Now this market is growing at a tremendous rate, but these systems are notorious in producing false alarms. Now these false alarms are of course expensive, not just for the police department, but also for the homeowner. So where do you put the intelligence though? Where do you put the intelligence? Do you put it inside the home, at the edge, or do you put this intelligence in the cloud? If you do use a hybrid architecture where you partition the system and put it on the edge as well as cloud, how do you do the partitioning? How do you create the system partition to put the right intelligence in the right location? So there are many possibilities here. So let's look at the first possibility. This is one of the hybrid architectures. Here you use inexpensive dumb camera at the home location. And then you upload all the frames that you see from all the cameras up to the cloud. And the cloud does the motion detection, the object recognition, and the highlighting of events. Now you can see here the bandwidth required on the network is pretty high, because you're basically sending every image up to the cloud, and most of these images are pretty boring, static images where nothing is really going on. Now you could use yet another hybrid architecture, and here you could move the intelligence to the camera. So the motion detection can happen at the camera, and you only upload some of the relevant images. Wherever you see the motion, you upload the frame to the cloud, and the cloud would do the object recognition and highlighting of events. So two different architectures, two different partitions, but there could be yet another solution. So this is a hybrid of the first two solutions, where you continue to use dumb, inexpensive cameras that only do image capture, but then you put in a mid-tier server that does some of the intelligence. And the server does the motion detection. And it sends only relevant images up to the cloud again, where you can do object recognition and event highlighting. Now, what you've done is you use the inexpensive cameras from the first architecture. You use the fact that your bandwidth is requirement is going down because you're only sending the relevant images, but you added the cost of the edge server at the home. Now there are benefits to the edge server. You can archive the images locally as well. right? So you can see there are many different architectures possible. You can partition the system at different locations, and a lot of the partitioning would depend on the economics of the situation as to where you do the exact system partitioning. So let's look at some of the challenges involved with creating these hybrid architectures. What are the factors involved when you decide the architecture of the system? So compute throughput and storage capacity, of course, is a huge advantage when you do the processing in the cloud. And that's why I've colored them green. But if you send a lot of data up to the cloud, like in our architecture 1, where you had dumb cameras and mostly all of the images were getting uploaded into the cloud, you incur the bandwidth cost. Depending on the instance that you use for the cloud also, you could incur a significant amount of platform as a service cost. So that's a factor in deciding what to put in the cloud. Also, your application needs to be developed on the cloud, so you have software development cost on the cloud. So these are some of the factors in deciding what to put in the cloud. On the edge processing side, low latency and the ability to combine different sensors into a single data stream is a big advantage on the edge side. Also, most of the processing, if it's done on the edge, you have a lower bandwidth requirement on the network. And finally, of course, because you're putting the processing and the data at the edge, the risk of data breaches is lower at the edge side. But at the same time, you have to develop your hardware for the edge processing. So you incur a hardware cost. You have to build the board, you have to do the system yourself. You're not using a cloud instance. You're not going over and calling an API in the cloud. So you have to incur the hardware cost. You also have to look at software and hardware cost development, because you're doing some of the development, the hardware cost, and some of the software development on the edge yourself. And because some of these systems reside in an embedded system, you have a power envelope to work with. A lot of times the power constraints at the edge are pretty significant, and you need to be able to work within these constraints if you have a lot of intelligence that you're putting in the edge. So there are a lot of factors involved, and you need to blend these factors together, and the factors could change over time as well. With more research and more different algorithms and coming in, you need to account for these factors, and you need to blend them together as you decide your hybrid architecture. Let's look at some of the other challenges. So once you decide your optimal architecture, hybrid architecture for your processing, you need to pick the right edge device, and you need to pick the right cloud instance to work with. In terms of the edge devices, there are many choices for you. The choices will be ASSPs, FPGAs, or GPUs. And there are many of them. You can see the ASSPs being produced by all the big companies, TI, NXP, NVIDIA, Xilinx, and so on. Now, each of these devices, they will come with its own software stack. So if you're working with TI, you have Code Composer, you have NVIDIA, you have Jetson, you have Xilinx, you have SDSOC and Revision stack. So many different software stacks to pick from as you pick your devices. So you to account for the software stack you need to work with as you pick your edge device. Once you pick the edge device, you need to pick the right cloud instance. And you have many choices there as well. You could use APIs from Google Vision API. You could use AWS Recognition API, and many others. But you also may need an accelerator that goes with the cloud. So you may need a custom accelerator that goes with the cloud, and these accelerators could be based on CPUs, GPUs, or FPGAs. And these accelerators themselves could come with different software stacks. So there are a lot of choices here. A lot of edge devices, a lot of cloud instances, custom accelerators. You have to blend all of this together to decide what is the software stack, what are the types of solutions you want to use to be very productive. Here's another challenge that system designers are facing. The system designers need to keep up with the research in deep learning. Deep learning has been around for a long time, neural networks research goes back to 1958. For the first 40 years, not a lot of interesting algorithms came out of that research. A lot of that research went by the wayside. Nothing really significant that can be deployed in the industry. But for the last few years, last 5-7 years, there's tremendous progress in this world on deep learning. More and more new applications, algorithms, models are being created, and there are more and more algorithms that are application specific. The speed at which academia can produce a neural network, and that is industry, there's something that industry can adopt, is growing at a very rapid pace. From academia to industry, it only takes about 6 months to deploy a neural network now. So your system designers need to be able to keep up with this research and be able to handle the rapid pace of innovation in this world. There's also a lot of research that is going from floating point computation in neural networks to fixed point, lower and lower precisions in inferencing that you need to account for in this world on deep learning research. Okay, just as with research in neural networks and deep learning, there's a lot of work going on in the sensor world. The number and types of sensors that are being produced and number of applications that are able to fuse data from these sensors is growing at a rapid pace. If you look at an autonomous vehicle, it has to fuse data from lots of cameras, rear camera, forward camera, side cameras, radar, LiDAR. They may even fuse data from audio sensors so that they know if there's an emergency vehicle coming in. So a lot of research in sensor world as well. The choices you make need to account for research going forward. You need to be able to keep up with this research, because if you may be deploying a solution today that could get obsolete tomorrow, right? So your hardware and software needs to be resilient to a lot of this research that is coming out. So let's look at what's needed. We've seen a lot of challenges. There are a lot of factors involved in picking your hybrid architecture. But what's really needed to keep up with this dynamic nature of research in this vision world, and what's needed to be able to cope with the complexity of the vision world. So one challenge we did not talk about is the fact that process node is not able to give you better CPU performance. Now here's a famous chart which talks about single-threaded CPU performance, and you can see it's flattened out in the last few years. So you're not getting more and more CPU frequency and not able to boost your performance just using a newer CPU. But at the same time, there are a lot of workloads that need the performance boost and need the latency improvement. You can see a lot of work in video transcoding, machine learning, deep learning, and a lot of analytics needs a performance boost, and they need better latency as they move forward. But it's not coming from the CPU. So what you truly need is custom accelerators that are application specific. And that's true on edge as well as on the cloud. So what your hardware needs to be able to do is the hardware needs to be adaptable to be able to create the custom accelerator to get you the better performance and get you better latency. So your hardware needs to be adaptable. So what you also need to do is be able to have your solution keep up with research in deep neural networks, DNNs. So give me a minute as I talk a little bit about DNNs. Bear with me here. This is a neural network that is AlexNet, very old network that is used a lot for benchmarking these days. It's used for image classification. You can see this is a pipeline of convolutional layers, and a lot of the computation here is done in stages in a pipeline. There's a lot of research that has shown now that you don't need to use floating point computation to get accuracy in the inferencing world. There's training and there's inferencing. Inferencing is when you deploy these neural networks either on edge or the cloud. So already a lot of research shows that we can get to 8-bit precision to get to the same amount of accuracy that you can with a floating point computation. But latest Stanford research has shown that you can actually go much below 8-bit. You can get to about 4 bits in the first few convolutional layers and get the same amount of accuracy. So you can see here a chart of accuracy versus number of bits in your weights in your convolutional layers, and it sort of saturates beyond 4 bits. So going beyond 4 bits, using more than 4 bits does not really truly buy you accuracy in your network. At the same time, if you look at the later layers, if you look at what they call them fully connected layers, it doesn't make sense to go beyond even 2 bits of precision to get you better accuracy. So your hardware needs to be able to handle variable precision to get the optimal network on your hardware so you can get better power and better cost. So that's another requirement of your hardware. Be able to keep up with variable precision to do better power, better cost deep learning algorithms. Well, there's yet another research from Stanford that talks about pruning of these networks. You can prune away some of the nodes, some of the edges here. You can get a lot smaller networks after you come and compress the networks and get similar accuracy. So here in one of these examples, I've shown the neural network on the right side has been compressed down to 15% of area of the original network. So 15%, which means you can get a lot better power, a lot better cost, but you get the same accuracy. You can leave the area for the rest of your vision processing pipeline. So again, your hardware needs to be able to support sparse computations and be adaptable to support sparse computations of deep neural networks to get you better power and better cost. Okay, a simpler concept. Your hardware needs to be scalable. The hardware you pick ideally would be something that can go from edge, or rather endpoint to edge to cloud. It should just scale with your requirements. So you can partition the pipeline, the vision pipeline, at any point of time, right? And you can change the partitioning over time as well, and you can move the algorithms across the entire spectrum from endpoint to edge to cloud. Now, ideally, you would want the same software stack to work across all of these devices. So makes life a lot easier for the algorithm designers, for system designers, to have a scalable architecture that can go from endpoints to edge to cloud, right? And the more you go to the cloud and the bigger devices, you should be able to get better performance with your devices. So I've shown you lots of factors involved in creating these hybrid architectures, a lot of challenges, some of the solutions, but it's probably clear that what you really need is a system modeling tool. All of this today is done on spreadsheets with some amount of intuition, but what you really need would be a system modeling tool that can take into account some of these factors: payload sizes, max latency, bandwidth requirements, platform as a service cost, and maybe even what is the cost of creating these hardwares on the edge, and then put it all together and sort of guide the system designer as to what should be the partitioning at this point of time. There is no such tool in that I've come across, and if you know of some of these tools, I would like to know. But this would be an ideal solution where it would do the profiling, it would do sort of the guidance to the system designers to come up with the right solution. Okay, so in summary, I'm truly excited about this world, the Vision world. Like I said, we were the founding members of Vision Alliance. It's great to see the conference grow as much as it has. There are a lot of possibilities ahead of us. Deep learning is truly, sort of the driving force behind some of this growth for us. I have shown you that we need scalable, adaptable hardware architectures that can go across edge to the cloud and be able to do some of these vision processing pipelines. Ideally, we would also have a unified software that you can work across all these different solutions. I didn't talk about this, but yes, it's extremely critical that we all collaborate. We collaborate on some of these new industry frameworks, standardize them, and on the libraries, open source them. That will only accelerate our growth. Here's one final sort of commercial slide for Xilinx. We do create adaptable, scalable platforms. We have, we entered this world, the vision space, with our Zinc processing device, which combines ARM-based processing and our fabric. We do production boards now. We are deployed on the cloud as FPGA as a service, so you can use us with APIs. And we do have a revision stack that allows you to create the vision pipelines. We are in a number of different applications in ADAS models, Pro AV, broadcast, drones, AR, VR, and so on. And we are, you can see some of the information on Xilinx. We are on Embedded Vision. We are a platinum member, and you can also visit us on Xilinx.com. We have a separate Embedded Vision zone in which you can see some of this work that we're doing. Okay, thank you.
Fantastic. So we have a good 5 minutes left, as planned, for Q&A. Anybody have any questions for Salil? Oh, here's a question. Yeah, you may want to come over. Here, let's use this guy here.
I wanted to ask thank you very much for a very interesting talk. I wanted to ask your opinion on how the co-emergence of 4G, advanced 4G LTE and 5G networks will modify actually these hybrid architectures, and do you think that will also give rise to a three-tier architecture, so not just the edge device, the intelligent edge device and cloud, but really the edge device, the mobile edge compute, and cloud compute?
So I guess 5G will change the economics of the partitions, right? Where it's a more reliable network with high bandwidth. So yes, absolutely. So that's exactly what I was saying. That at any point of time, the economics will drive the partition. 5G will bring in yet another sort of the research will drive a different economics in terms of what you need to put on the cloud versus what you may need on the edge devices. Likely, if 5G is truly successful, and it's going to take many years before the whole thing gets deployed. But yeah, I mean, there could be potential for a lot more processing in the cloud and a lot more applications that are visible to the end user, but a lot of the processing is on the cloud. But some of the applications are for data privacy and for absolute latency requirement will continue to remain heavily on the edge, and there's no getting around that, right?
Yeah.
Okay.
Thank you.
Yeah.
Just a quick comment on that. One of my clients, we're working on 3D applications, and they're looking at moving from 2D to 3D vision, first of all, like stereo cameras, and then looking at adding machine learning. And machine learning is also very, very memory intensive. And so there was something like a 4x BOM cost potential improvement if you could move a lot of that processing out of the edge device itself and into a low latency thing between the cloud and the edge, which you're calling edge compute. Some people call fog compute. Depends on how you look at it. Microservers, like you said, that are close, or it could be through gateways, intelligent gateways and things. So that's a huge jump. And you today 2D processing, okay, maybe you don't need it, but just like we heard in our last talk, and I think we're going to hear in our next talk, 3D might take it over the limit, especially when you combine it with AI. 3D with AI is very compute intensive, and it's not all going to be done in the devices. Yeah, exactly. I think there could be a mid-tier, like I showed you, right? There could be a mid-tier cloud fog, you call it, right? Which can do some of the processing that could help you with latency. You don't have to go all the way to cloud. But 3D will definitely be yet another sort of step up in terms of the amount of data being created and the requirements on the bandwidth. Yeah, so, the demand's growing and the cost of the sensors are coming down, but yet the compute issue is not still resolved. So, and you can see the CPUs is not getting faster, and so you need a lot more accelerators to continue to boost the performance, right? So, absolutely, it's definitely an acceleration application. Any other quick question? One more, by any chance? Okay, Salil, thank you so
Okay,
much.
thank you.
Great job.